Okay, these are my final recap ones, I guess. We'll use these for posterity at some point, I presume. So here we go. We're going to go with review here. We're going to try to do these, talk generally now, and not talk so much for some of these exam or the last homework sets. First, the cable one. Let's really realize how straightforward a cable problem that's not a parabola is supposed to be. And so if basically what you always have to be given in one of these problems is a location of one of the points of application. The other ones, the reason that is true is because a cable is going to be responsive. It's a funicular structure. It's going to be responsive to the load. So these, as you change the weights, these are going to move up and down. They're not necessarily going to move that much left and right. And so when you've got here, basically you have weight 1, weight 2, and perhaps weight 3. And you can look at this, you can, as your origin right there, and you can say it's force times distance plus force times distance plus force times distance equals force times distance in your one radial vector up. And then you can solve that. Once you know that, you can then figure out what that is. Now all you need to know is what's left and right. You can't tell that except in here. If you know the direction of this cable and you know the up component of it, you can then tell what the y component is. If you know the cable's pulling there, in other words, if the reaction is pulling there, the cable's pulling down with the same amount. Here it's pulling back with the same amount, and now you have what is a concurrent force problem. You know this, you know this, you don't know this, but you know that this plus this equals 0. So basically you take this, slide it over, and then that becomes your unknown force there. You also do that, of course, by knowing that you can take and solve this by knowing that you know the sine, cosine of theta 1 and the sine of theta 1 in terms of its magnitude, and the cosine of theta 1 and the sine of theta 2. You can add these two, and this has to be the equal and opposite. So that's basically how a problem works that is a cable problem with suspended weights. You solve for the reactions by sum of the moments, and then you use a concurrent force problems, a series of them, to go across the structure, realizing that if you've got, like in a truss, if you've got tension here, if it's being pulling here, it's pulling out there. If it's compression here, it's compression here. You should have gotten that out of doing your trusses. So I'm going to go now then talk about kind of something we've talked about in the past, and that is a composite section. If in fact you have something with area, right, and then some area of steel, so the area total equals the area of the concrete plus the area of the steel. And the area of the steel is usually, is some reinforcement ratio times the area total. Now all that said, what you do is you take the area of the concrete plus some stiffness ratio, in other words, the area of this, or the E of the steel over E, or the modulus of elasticity of the concrete, which we know is around 9, but we can come up with a better number based on an equation that some of you may have seen on the board, something in the order of E sub concrete equals somewhere around 5,700 times the square root F prime sub C. In other words, the compressive strength of concrete. But you can come up with that and you get an area transformed. Now your stress is basically P over area transformed. That gives you basically the stress in the concrete. And the stress in the steel is just the stress in the concrete times that ratio reversed. So it's going to, that ratio, so it's something like 9 times that of the concrete. And that's because if you look at this in cross-section, if this changes delta L, right? If this section changes, goes from L to delta L, the steel is also changing from L to delta L. And if you have delta L over L, that's the same as strain. You know that strain, Y equals mx times the modulus of elasticity of steel is equal to stress. So that's how that mathematics goes. And that's, now there's not a problem set that does this next bit. I'm going to do it anyway. because it is of great interest, those of you who are interested in continuing on and learning after a month or 2 or 3 or 6. There's some incredibly great resources out here that takes you to the point where we are, from where you are here, without even knowledge of the CAD. That's the toughest thing about teaching a class like this, is you're trying to put the CAD skills together with the math, and it doesn't always work. I apologize if it didn't for you, but I have exposed you to enough other things that you'll be quite prepared to learn out at MIT or Mechanics and Materials at Michigan or whatever the case would be. So I'm going to go here and talk about the mathematics of the transform section in a reinforced beam. And that, of course, is if you've got something here and you get its moment of inertia, you can actually do the moment of inertia a number of different ways. If you want to get the moment of inertia of that, it would be the moment of inertia BH cubed over 12 of that minus the BH cubed of that twice. And that would give you the moment of inertia of this. You could also do it in mass prop. You could also do this. You could take BH cubed over 12 of that plus BH cubed over 12 of that plus BH cubed over 12 of that plus this area times this distance squared, and you'd have to do it twice. That is a parallel axis theorem. What you'll eventually see is sometimes this thing's spinning about itself up here. In other words, this has a height of h and a width of b. As you do your BH cubed over 12, that's really usually often not very much compared to this area, which is b times h times distance squared from the centroid. How does this work when you put steel? Well, if you've got some steel down here, particularly in the compressive zone, you have to expand the steel, which of course brings down your neutral axis and changes some of that equation of the moment of inertia, which is the sum of all the little areas times all the distances squared. So you've got it, all of a sudden you've transformed the distance in a couple of ways. So that's how you go about using the kind of same general concept of the relationship of the steel stiffness to the concrete stiffness, by expanding out and not up, and you get what's something called a transformed moment of inertia. There's a very interesting problem that is at least discussed, and you'll see it. That is if you've got a piece of wood, and it's usually not done in reinforced concrete, but if you have a piece of wood and you can put something glue something a lot stiffer onto that, how do you do the mathematics? Well, you compare the modulus of elasticity of the stiffer material to the less stiff. You expand that stiffer material. That, of course, makes this, instead of acting like just a regular rectangle, it makes it act like kind of a T-beam. It brings down your neutral axis and changes everything. So that's kind of the better. When you get into reinforced concrete, it gets a little bit more complex than this. But when it comes to wood, you can basically add some stiffness, some laminates of different stiffnesses, and you see that discussion when you start talking about LVLs and anything like that. All right. The last kind of bits of this I did in class, and I'll try one more time in the next 2 minutes, and that is the shear moment diagram. Basically, you want to learn the mathematics of it. You want to learn what we did in class in terms of you doing the matrix stuff and then forgetting what's behind you and shifting your coordinate system. But in effect, if you have the load curve, whatever that load curve would be, I'll do it again here. If this is the load curve leads to a reaction here. The shear curve begins there, and then it has a slope equal to the negative of the value of the load curve. And so the shear curve does something like this, where of course it has to come back to 0 at the other reaction here. And in addition to that, what the shear curve tells you is that wherever the shear curve crosses 0, the moment will be at a relative maximum or minimum. So it's something like that as your moment curve. So I'm going to go one more time. I think I did one in class, which was a point load. I've got a beam here of length L and a force P on there. Of course, the shear curve does this. This is P over 2. And this is P over 2. It starts at P over 2. The shear curve stays the same because anywhere you cut along here, you have an increased forces that you're resisting. It goes down along here and comes across here. Of course, that means that if this is P over 2 times L over 2, the maximum moment is PL over 4. That, of course, is another great one to use in addition to what we remember, WL squared over 8 for the maximum moment of uniformly distributed load. Thanks for listening. We'll call that a wrap.